So last time we talked all about the physical hardware, the guts of a computer. But here's the thing. All that amazing hardware is basically just a fancy rock without instructions. It's useless. Today we're going to pull back the curtain on software and code and see how a simple idea in a person's head becomes a real action that a machine can perform. Let's jump in.
Right, so you've got your CPU, your RAM, your storage drive, all these incredibly powerful parts sitting there. But what is it that actually tells them what to do? What breathes life into that silent collection of circuits and turns it into something that can play your favorite game or send an urgent email? Well, that's where software comes in.
And here's our game plan for today. First, we're going to start with a simple analogy, thinking of software as a recipe for a machine. Then we'll look at how our words get turned into machine actions. We'll follow a super simple program to see how it all works together, and then we'll get into the messy part, the very real risks that pop up in the real world.
To really get what software is, you don't actually need to think about high-tech stuff at all. Nope. We can just think about something way more familiar, like, say, cooking.
I want you to think of software as a really, really detailed recipe. And the hardware, specifically that CPU we talked about, that's the chef. Now, this chef is incredibly precise. It doesn't guess, it doesn't improvise, it just follows every single instruction. Add 1 cup of this, mix for 30 seconds, heat to 350 degrees, exactly as written, one after the other. That's all software is, a long, precise list of commands that tells the CPU what to do with all the other hardware to get the job done.
Okay, so if software is a recipe, we've got a bit of a problem. The chef, our CPU, doesn't speak English, or any human language for that matter. So this next part is all about the crucial translation step that makes this whole thing possible. See, on the left, you've got what we call source code. It's written in a programming language that a human developer can actually read and write. But on the right, that's what the CPU understands. It's called binary code, and it's literally just a stream of ones and zeros, representing on and off electrical signals. There is a massive, massive gap between the two.
So how on earth do we bridge that gap? We use a special program called a compiler. You can think of the compiler as our master translator. It's a genius at taking that human-readable recipe, the source code, and translating it perfectly into the only language our chef, the CPU, actually understands.
So this whole process really boils down to 3 key steps. First, you've got a developer who writes the source code, the recipe. Second, the compiler does its magic, translating all that code into binary. And third, the final output is something called an executable file. That's the actual program you double-click to run on your computer.
Now, this is where things get serious from a security perspective. If a hacker can get their hands on the source code, it's like they're poisoning the recipe before it even gets sent to the kitchen. They can sneak in malicious instructions right at the start. This is why protecting source code is so unbelievably critical. It's the blueprint for everything the computer is about to do.
All right, enough with the theory. It's cool, but let's actually see this happen. We're going to follow a tiny, tiny little program as it runs and see how it gets all those different hardware pieces to work together. We're going to use a super famous first program that every coder learns. It's called Hello World. But we'll add a little twist. Our program is also going to do some simple math. It's going to add 1 plus 1. By doing just these 2 little things, we can see the whole hardware orchestra in action. Okay, so the very first instruction hits the CPU. This is what it was born to do, compute. It takes the number 1, adds 1, and gets the result. This is the absolute core job of the processor, whether it's adding 2 little numbers or crunching massive, complex financial models.
But where does that answer go? It can't just hang out in thin air. The CPU immediately places the result, the number 2, into RAM. Remember, RAM is the computer's short-term memory. It's scratchpad. The answer sits right there, ready for whatever the next instruction is.
And for our final step, the program tells the computer to save the message forever. The CPU commands the storage drive to create a new file called log.txt and write the hello world message inside it. And there you have it, the perfect chain of command. The CPU computes, RAM holds the work in progress, and storage saves the final result, all of it directed by just a couple lines of code. So far, everything we've talked about is how software is supposed to work, in a perfect world. But as we all know, the real world is anything but perfect. It's messy, and that's where risk comes flooding in.
This is one of those fundamental, absolute truths of technology. I don't care who wrote it. Every single piece of software can have mistakes in it. We call them bugs. Sometimes they're just little typos that don't do much, but other times they can be absolutely catastrophic security vulnerabilities.
And that leads to a really crucial point.
When a piece of software stops getting updates, when it's unmaintained, that means nobody is fixing those inevitable bugs anymore. It just sits there, vulnerable. That piece of unmaintained software on your network, it's a permanent, unresolved risk just waiting to cause a problem. And it gets even more complicated. You see, most modern apps, they aren't built from scratch. Just look at this. It's pretty typical for only about 20% of an application to be original code written by the company. The other 80%, that's all code pulled in from external third-party libraries, kind of like pre-made building blocks.
This creates a massive problem we call supply chain risk. Think about it. If one of those third-party building blocks has a security flaw, then every single app that uses it automatically inherits that same flaw. This is exactly why the idea of a software bill of materials, or an SBOM, is becoming so important. It's basically an ingredient list for your software, so you know exactly what you're using.
And to wrap our heads around this, let's look at one final concept. Software isn't just one big thing, it's built in layers. At the very bottom, you have firmware. That's code embedded right into the hardware itself. Sitting on top of that is the operating system, like Windows or Mac OS, that manages everything. And then way up at the top, you have the applications you actually click on and use. The critical thing to remember is that each layer completely depends on the one below it.
Okay, so let's do a quick recap. What have we learned? 1. Software is the recipe that brings hardware to life. 2. Human-readable code has to be compiled into a machine language that the CPU understands. 3. All code can have bugs, and code that isn't maintained is a huge risk. 4. Most apps are built with third-party code, which creates a big supply chain risk. And finally, real security means you have to think about all 3 layers: firmware, OS, and applications.
So I'm going to leave you with this final thought. We're all pretty good at updating our apps. We get those annoying pop-ups to update our operating systems. But what about that bottom layer, that foundation? When was the last time you or your company actually checked the firmware on your devices? Because at the end of the day, your security is only as strong as its lowest layer.